So sometimes it might feel primitive to keep on doing this recursive calls, right? From main 7 I again call main 7, from readints I again call readints. Okay, that looks like a very primitive way of doing repetitive action. So Haskell allows you a multitude of ways in which you can repeatedly perform actions. I'll look at only 2 or 3. Okay, one of the simpler ones is something that's also cool. It's called forever. It just says repeat it forever. Okay, but if you are repeating it forever, how do you exit something, right? That is the nice thing. So there are ways in which you can exit. Use forever to repeatedly perform an action, but forever now is not part of basic Haskell. You need to do you need to import this control.monad, and we will see that we are going to introduce import a lot of things from control.monad for slightly more advanced input output. So forever is something that says repeat this block forever. Okay, but the block itself should have some way of signaling when to exit, and that is given by one of the ways in which you can exit is to use exit success to exit the loop. Okay, and that requires import system.exit. Okay, so now you have system.io, system.exit, control.monad. Okay, there are 3 things from which you are importing. Okay, exit success says, oh, I am exiting successfully. There is also an exit failure, but we don't need it here. Okay, and you check when to exit using eCof. In a kind of a thing where you are explicitly doing a recursion, that is the most primitive way of doing it. You don't need to say anything about exiting a loop, because if there is a branch where you come to the last line of the branch and it's not a recursive call to the same function, then you are exiting. Okay, there is let's go back and check. When will this function exit? If exit condition is true, then it says return empty list. This return, remember, is not the return of your imperative languages. This is just, that's why when I wrote the programs, I wrote it explicitly as pure empty list, so that you don't get confused. But this, at this point, the function will this read int list will stop, because you have reached a branch where you have reached the last line of a branch, and that is not a recursive call to some there is no recursive call to the same function. Here also, when you reach this return x colon x's, you will stop. Okay, and that's because the recursive call happens before that. Okay, so you first make a recursive call, then once the recursive call returns, you do x colon x's and promote it. Okay, the point that is the point there. But here, so here you controlled repetition by explicit recursive calls. But with forever, you are going to put the whole do block inside of forever, so no matter what, it will happen forever unless you explicitly tell when to exit. Okay, and that is done by using exit success. You check for when to exit using eCof, but you signal exiting by saying exit success. Let us look at the code here, right? This is the code. You say import system.io. This is for eCof. You use system.exit for exit success. You use control.monad for forever. Okay, so these are the 3 imports that you need to do. So now the program is much simpler. There are no explicit recursive calls, etc. All you are saying is forever do the following: check if eCof has been reached. If so, then exit success. Else, do read a list of integers. Okay, so here I am doing a different action. I am in each line I am reading a list of integers and immediately printing the reverse of that list. Okay, I can do all kinds of things here. So I am reading an input, I am reading an integer list and printing its reverse. Okay, and then again going back and try to read. When will I exit? The only time I will exit is when Control C has been pressed. Okay, and I check every time, and when Control C has been pressed, which means that the exit condition has been reached, I explicitly move out of get out of this loop by saying exit success, because this forever is a loop. I have actually put a do block inside a loop. Earlier there was no loop, there was just a do block and there were recursive calls inside the do block. Okay, that was an indirect loop, if you will. Okay, now it's an explicit loop, but this is a kind of a simplest kind of loop. I am repeating some block forever. It is up to the block to figure out when to exit. Okay, that is the kind of loop this is. Okay, we'll program this in a bit, or maybe we can program this right now. Let me just go to the VS Code and program this. Okay, we are here hw.hs. Let me just go and add a bunch of imports. Import control.monad and there is something called when, which is there in the slides, but I will introduce it right now when I write this code. And I will also do import system.exit. Okay. Now, I should call this main 8 because I have a new main coming up. So, this time what I am going to say is, I will just call it main 9 because it's fine. Forever do this. What is it? Exit condition is the result of the ECOF check. And now here is where the new thing that I wanted to say, when exit condition. So rather than saying if then else, okay, I can say when exit condition and I can immediately give whatever has to be done during the then branch. And rather than writing an else branch, I will write the rest as normal code. Okay, this is a nice pattern because you want to just handle the exceptional conditions and take some immediate action, and the rest is like the normal flow of control, if you will. Yeah. So when exit condition, I will exit success, and the rest is normal code. There is no if then else. So now what will I do? I should read a list of integers. I can actually do that also. Read line IO list int is what I am doing, and I am printing the reverse of the list. That's it. So this is nice. So let's try to check how it works in. Yeah, I in fact I should just call it. I'll have one main and which I'll keep renaming to different other mains. Then that's the simplest thing. Let's compile this in the shell and okay, this is compiled. Let's try hw.exe. Actually, because on this machine it's slow, I will actually do one small thing, which is that I'll put a message saying I am starting. Then I'll know whether the delay is being caused by the late start of the program itself or because the program is waiting for user input. Let's compile it again and let's now run it. Yeah, it should print out starting at some point. Yeah, so it's now started. So now I should provide lists on each line. Okay, so let's say 1, 2, 3. Okay, 123 I printed because this thing. I shouldn't say starting inside the forever block. That's a mistake. Let's go and fix this. Let's say Control C. Okay, let's actually make this nice. Okay, so before I start the forever, I should say right? And then inside the forever, that's a block of its own, and I should indent all this. Okay, and now once it's done, I can say exiting goodbye or some such. Okay, this actually is more like a input output program that you might have been used to in some other languages. Let's see how there is a loop inside, which is the block inside the forever, and there is a way to exit that by pressing Ctrl C. But otherwise, initially I am printing a message, and at the end also I am printing a message. Let's see if this works properly. Okay, so let's do this. Yeah, it started. So let me print, let me provide my inputs. 1, 2, 3, that gets printed out as 3, 2, 1, 4, 5, 6, 55, 2, 3, empty list, reverse empty list. Now I got bored, so I'll press Ctrl C on Windows, and you have to figure out what is the corresponding key on other platforms. Okay, Ctrl C I am performing. Okay, so it's not because it automatically exited. Okay, so that's another problem, right? So you are asking it to exit, so it won't even go out and print the thing that I am asking it to say later. There is no way to just exit the loop, it just exits the whole program. Okay, so at least for the moment, let us fix that by saying when exit condition, you can actually do this here. You say when exit condition, do put string line followed by exit success, and this thing here need not be there. Okay, so this is the thing. Okay, and I need to close the it's here. Okay, good. So this is done. Now let's try once again. Yeah, so okay, this works good. So let's wait for it to say starting. Yeah, okay, so now let me just say 1, 2, 3, it prints out 3, 2, 1. Let me say empty list, it prints out empty list 44, 55, 66. Yeah, now I'll say Control C. Yeah, it will say exiting goodbye and it will get it. Okay, so yeah, so there are no nested loops and exiting out of the inner loop and going to the outer loop, etc., that kind of thing yet. Okay, this is not the style in Haskell either. Okay, so the kind of things we have seen is actually versatile enough. Okay, already we have seen enough that will let us program many nice things. Okay, let me now go back to the slides and show a few more things. Right, as I mentioned, you can use when, and this I showed in the code itself. You can use when rather than if then else, and now you can have a simple thing like this. Okay, yeah, so that's one thing. Now I mentioned typically this should work, but on Windows I need to figure out how to do this. So one of the simplest ways in which you handle files is to say that so files, why are files important? Because you cannot always expect the user to keep entering something one after the other. You might want to handle huge data in which would already be provided in a file by someone, and you want your program to just go through the file and read it. So far the way we have done it is we've expected the user to enter one line after another, and we do get line repeatedly and do this. So the nice thing with Unix like systems is that the same thing will work for file input output also, except that when you invoke the program, you invoke it by using input output redirection, and this is how it works. So usual input is standard input, which is the keyboard, but you can always do input redirection by doing whatever your program is and say less than input file, means that all the input will come from the input file rather than the standard input. And similarly, the standard output will go to the screen, but you can always put the output in a file, write the output to a file by saying my program greater than output file, and you can of course combine these two by saying my program less than input file greater than output file. Okay, this is the Unix thing. We'll see about Windows, or you can try to figure it out for Windows on your own by searching your documentation for your local system. Okay, this is it. Okay, so this is the basic file IO that we will see in this course. We won't be saying anything more beyond this because we still have a lot more to do with Haskell. We want to see nice algorithms implemented in Haskell. That will be in the coming weeks. Okay, so far we have seen basic Haskell. Now we have seen one basic part of Haskell, which is IO, which we will be repeatedly using in testing our later programs. But the later part of the course will heavily concentrate on data structures and some algorithms. Okay. Okay, so here are two other things. There is a for loop in other languages. Now here there is a nice for. It's called for m, and it stands for monadic. And the way it is, this is like the kind of thing that some languages might have. For so this is really like saying for I equals 1 to n. You might have for I from 1 to n do something kind of loops in other languages, but actually the versatile kind of thing is for I in, and you actually give a list. For every element in a list, do something. This kind of for is also provided in languages like even Java, Python, etc. Okay, and that same thing is what is here. You say for again you need to use control.monad for this. For monadic and for, there are two variations for this. For monad, for m and for m underscore. Yeah, what are you doing? This is a nice this thing. What you are doing is you have a list of strings as an input, and for every string in the list, you are actually doing some input output action. Okay, and that is for m. Okay, and what is the input output action you are doing? You are reversing the string and putting it on the screen. Okay, that's what you are doing. But what it will do is its output file is a weird thing. We can actually demonstrate this in GHCI itself in a minute or so. Its output file for m will for m of any IO action where act, let us say, where access is of type list A and act is of type A arrow IO unit, let us say, what for m will do is it will do all the actions, one for each string, but it will also accumulate all the results in a list. Okay, but in this case the accumulated result is a wasteful result because put string anyway produces a dummy value as a result, namely the unit value belonging to the unit type. It has no significance at all. So what you will see is a list of unit values, a list consisting of open parenthesis, close parenthesis, open parenthesis, close parenthesis, etc., repeated so many times as there are elements in the input list. Okay, so that is what will happen. So what for m underscore does is to ignore the is to not accumulate the results in a list. Okay, so it's so for m of access act, suppose access is of type list A, act is of type ARO IO unit, for M access act will be of type IO list unit, and that's a useless list really, right. For M underscore access act will just be IO unit, okay. It will ignore the, it will not accumulate all the results, it will just produce this thing. We will see that both of these have their, both these forms have their use, but for the moment I will just show you for M and for M underscore, yeah, in a minute. Let me just go to VS Code now, and let's go to GHCI itself directly, okay, and let me import control.monad. I can do that in GHCI itself, and I can now ask for the type of for M. It might not make total sense at the moment because it will refer to some monads and so on. Yeah, so this is not really making much sense. So I can ask T plus D. Plus D will give a default type, okay, rather than the most general type. Yeah, it's saying as long as M is a monad, when it says monad, you can think of it as IO, okay. So list A arrow IO B arrow IO B, IO list B, okay, that is what this is. Whereas for M underscore will be list A arrow IO B arrow IO unit, okay, that's what it is. So let me just illustrate. Let's take for M and then now I will use a list of integers, and I will have a trivial this thing. I will say a print dot I don't know, so give me some function plus 5. So I am going to add 5 to every number in the list, and I am going to print it. Printing is an IO action, so I have to use for M. You see what happens? Yeah, what happens is that every number you add 5 to it and you print it, 6, 7, 8, 9. Print also prints a number and then puts a new line, so it's all printed one on each line. Your input was a list, but you have a bunch of actions now, but it has wastefully also collected all the return values which are just units into one long list. So if you want to ignore that, you just do for M underscore. Okay, now nothing will be produced. So the accumulated return value will be ignored. So now this is a very useful thing. Recall that you had a map, and in fact, now that I am mentioning this, remember that you can do something like this with lists. Map plus 5 1 dot 10. Right, but what it will do is it will apply the function on every element of the list. This function is a pure function, so it will produce an output list. But there is something called map M underscore, let us say for now, and I say apply this function print dot plus 5. This is an IO action. So map M underscore is a monadic map. It will take an IO action and apply it on every element in your input list. Yeah, so now it doesn't just produce the list as value, it actually does all these actions, okay. And I can also do this for my original thing that I was mentioning in the slides, print dot reverse, or I could even say put string line dot reverse of, I don't know, give some ABC. Okay, so it's reversing each line and printing it, CBA, FED and IHG, okay, that's what you get. So mapm is this, for M is the same as mapm except with the order of the arguments reversed, okay. So the same above thing I can write as, if I use for M underscore, and I will first give the list and then give the action. Yeah, whether you first give the action or you first give the list, that is the only difference between for M and mapm. Okay, so now you get this. Okay, and yeah, so I said print dot reverse. If instead I had said put string dot reverse, there wouldn't be the quotes there. Put string line dot reverse. Okay, so for m and map m are very useful if you want to repeat some action on every element of a list. If you want to repeat an action 10 times, let us say, suppose I want to do some, I want to say Haskell is cool 10 times, let us say, then you could actually do this for m 1 to 10, right? And then I want to write an action, and this action is supposed to act on the element of the list, but it's going to ignore the element of the list. So backslash underscore, remember this is a lambda, and if in the lambda you are not using the input variable, you can put an underscore, backslash underscore arrow, what do you want to do in this case, print dot plus 5. No, you want to say, you're not even going to use the input, you want to say put string line Haskell is cool. Now this will print 10 times Haskell is cool. Let's see. There is some problem because of no, it's fine. I don't know what the error is. Let's see. Yeah. Yeah, so it's now saying Haskell is cool, Haskell is cool, Haskell is cool 10 times, right? But this is again, so I want to repeat something 10 times and I have to give the list 1 dot dot 10 and I have to do this. There is a much more direct way of doing it, and that is recall once again that there is this function called replicate. Let's see if it's loaded already. Yeah, it's of type this int arrow a arrow list a. What it will do is it will replicate an element 10 times. So if I say replicate 10 5, it will create a list of 10 5s. Okay. So just like I have map and map m, I can have replicate and replicate m. So I can do replicate m underscore 10 times put string line this is the same as saying for m from 1 to 10 do put string line Haskell is cool, because that's a roundabout way of saying the same thing. Here you are saying repeat this IO action 10 times. Recall that we actually had a n times thing that we implemented earlier. This replicate is exactly that n times that we had, okay, in the thing. So this is actually built in. So you can use replicate m underscore. Replicate m underscore will not collect all the result values and produce them. If I used the same thing without the underscore, then I will have a final line which will be a list of 10 unit values, you see. So it depends on when you want to use replicate m and when you want to use replicate m underscore. Let's check this. In the slide, see, I can actually say here I want to use replicate m underscore, right, because I want to just get and put is something where I am getting a line and immediately putting its reverse. Okay, here I am replicating it 10 times. Here I am just getting 10 lines and creating a list of strings. For that I need to use replicate m, because here no replicate m underscore will not work because I have to accumulate the resulting values. Okay, let me test this on the GHCI. Replicate m 5 times, let us say get line. Okay, now I will have to say various things a, b, c, d, f, g, h, i, j, k, LMNOPQRST. Let's see what happens. Yeah. So now I have a list of length 5, and each element is the subsequent line that you have read as your input. Okay. So this is very useful. Okay. Replicate and replicate, replicate m and replicate m underscore, for m underscore, map m underscore. These are some very useful input output routines, which actually help you do a lot of nice things very quickly without explicitly writing your own recursive blocks inside a recursive code inside a do block. Finally, this is part of input output because it's because you this involves some interaction with the real world. I'll tell you why, but this is a very useful thing that we will see, that we will use multiple times in the next part of the course, and that is randomness. Okay, you want to generate random values. For that we will use two routines, one called random IO and another called random RIO. Okay, random IO will produce a value of type A. Random RIO, R stands for range, produce a value of type A from range L to U. Okay, so that is the and of course, if you for applying random R, it should be a type that belongs to the class enum. Okay, it should be A should belong to the type class otherwise there is no point of enumerating from here to there. Okay, so anyway, so this is just upper bound, lower bound. Okay, and maybe not, maybe it doesn't need to belong to enum, but anyway, so this is specifying upper bound and lower bound. Okay, so I need to verify this, but for now just think of pick a random value of type A from such that L is less than or equal to A, less than or equal to A. Let us just put it that way. Okay, and you can combine this randomness with replicate m to produce random lists. This is the nice cool thing. So for instance, here I want to produce a list of random integers. What do? I just say rand int list size. That is the name of my, this is rand int list is the name of the function. Size is the one integer argument that it takes, and all you do is replicate m times, replicate size number of times the following IO action. What is the IO action? Random IO. Random IO produces a value of type A, but the value of type A is clear because I have mentioned the output type here, IO list int. So it will clearly do this. Similarly, if I want a random string of where each character is English character from which is lowercase, then I can do something like this. Rand string is replicate m size number of times, random RIO pick a character between the range small a to small z. Let me just show you how it works in GHCI, and this is very useful. You don't need to remember all these things, this is just for extra this thing, but we will actually be using this in doing many tests for later data structures and so on that we will teach later, and you can also use this very effectively in various tests that you do, okay, as you program more and more complex things. Let me just show you random string and random int list in VS Code. I will program these two things, and that will be the end of this lecture. Okay, so let us go to VS Code and do this. Let me go to hw.hs again, which I have. It has lots of things. That's fine. Let me just say rand int list. Rand ints. I can't call it rand ints. That's read ints. Okay, rand ints. But for all this to work, I need to first say import control.random. Again, I have not introduced too many extra things, but these are some these 4 or 5 things. You can just note it down somewhere and you can just use it freely. Okay, so other than this, I won't talk about many mysterious Haskell libraries and functions that you will not control.random but system.random. The reason randomness is IO is because you want to just pick a random number. So what it will do is it will depend on some I don't even know, maybe some physical characteristics of your machine even, okay, to pick some random number, okay. So it will pick an initial seed and then it will generate further random numbers from that, but anyway it has some interaction with your system, okay, to read a first value, okay, some random value first, yeah, and that's why it's system.random, and what I want is random IO and random RIO. Okay, good. So now let me go down, and here rand ints int arrow IO list int. Here I would use replicate m and not replicate m underscore, because the list of values that are produced actually matters. Okay, so that's it. Let's see if this compiles. This time we can just do it in GHCI itself. Okay, I need to do replicate m also. Yes. We have only oh, we have not done for m replicate m or whatever, so let me just do it. Okay, great, it compiles now. Let's now try randints of size 20, let's say. Yes, very nice. So you get something. Now, because I said randints, it's giving me some really random integers. Some are negative, some are positive, but they are all huge. You can actually control the range once again. So it is best to use yeah, so you can also ask the user to provide the lower bound and upper bound as parameters, and here you say yeah, you pick a random IO, you become a random number in the range from L to U. Okay, and while we are at it, we might as well remove the import of random IO. Not that we are trying to be very efficient or something here, but okay, so this is done. So let's just check what happens now. Let's reload the program, the file. Okay, then now I need to give size 20, let's say, and numbers between 0 and 100, let's say, or minus 50 and 100. Now I get a random list. Now remember that something I mentioned earlier, referential transparency, which means that any expression means the same thing whenever you invoke it. That is not true here, because this is not a pure function, right? This is a function which is trying to produce a list of random integers. So if I again make a call to randoms 20 minus 5099, I should actually get a different list, and lo and behold, I get a different list, right? And similarly for rand string of size 20, 30, let's say, whatever. Yeah, this is really a random string. I could ask the same thing again and I'll get a different random string. Okay. Okay, so I hope you've learned enough concepts in this in these lectures. Input output is really useful. Yeah, we'll be looking at more programming, more data structures and algorithms, and we'll be using input output every time just to test those programs. But as you learn more Haskell and in an industry setting, you would perhaps be doing programs that are more heavily input output oriented, IO oriented. But still, the nice thing that Haskell provides you is that you can separate out code that is purely functional, which is only to do with computing a Fibonacci number or a factorial or whatever. Look at this code here. When I try to do this factorial, I don't need to worry about input output, etc. All the input output behavior is in these blocks where I try to actually interact with the user, okay, and I can just call these pure functional programs. So you'll have a lot of things. If you have a large project, you will have a whole bunch of pure code where you are just computing various functions of you are just computing various values on various arguments, and there will be some portion where you actually do interaction with the user or with actually some input files and output files. This is input output is quite rich. You can actually try to open some file in certain modes, try to write to them, etc., etc. You can do all that, file IO, etc. But right, so you would have seen it in other languages and it is easy to pick up. You've seen the rudiments of input output in these lectures. You can learn more on your own or later, in if time permits, in a later lecture. Okay, thanks a lot.